Have you ever felt an earthquake?
Yeah, living in Southern California, I felt a number of earthquakes.
So what did you do when you felt the earthquakes?
Of course, I did the thing that you're supposed to do. I dropped, covered, and held on to a sturdy structure like a table.
Okay. So wouldn't it have been nice, though, if you had a little bit of extra time before the earthquake shaking started to get under the table?
Yeah, that's true, because I just reacted once I felt the shaking start. But to truly prepare and mitigate damage from an earthquake, you'd like to know before the shaking gets to you.
Right, so with that in mind, we want to think about how fast seismic waves are traveling. So when an earthquake happens, there's slip on a fault, and that releases seismic waves in all directions. So if we knew how fast they were traveling, we'd know kind of when they approximately got to a certain place and when the shaking started.
Based on the distance.
Right. So that brings us to our good friend, the rate equation.
Okay, let's take a look at how fast these waves are traveling. So here's a travel time curve which describes the average velocity of the P wave and the S wave in terms of distance and time.
Right, and so we know that our rate equation involves both distance and time, so we have the information that we need here.
Okay, so how should we go about calculating the rate?
So, for example, if we're looking at, say, the S wave here, we want to determine it covers some distance in some amount of time, so we need to write down those two things.
Okay.
So let's say we pick a distance here.
So I'm going to pick this point here because it nicely crosses one of our grid lines.
Okay, so we can see that that point that you picked, if we draw our line down here, that is 30 kilometers. So the S wave at that point has traveled 30 kilometers. But we want to know in how much time has it traveled those 30 kilometers.
Okay, so we can trace over to the y-axis.
So if we trace over there and we look at the intercept here, that is 9. So 9 seconds. So that means that that S wave has traveled 30 kilometers in 9 seconds.
Okay, so we can write our rate equation, which is rate equals distance divided by time.
Exactly. So if I do that here, rate equals distance divided by time.
So our distance was 30 kilometers.
Okay.
And our time was 9 seconds.
All right, so we have 30 kilometers divided by 9 seconds. And what does that give us in kilometers per second?
So that's about 3.33 kilometers per second.
Okay, so that is our average S wave speed.
Okay, let's try for the P wave.
Okay.
So for the P wave, I see it crosses a nice grid line right about here.
Okay, so I'll go ahead and draw in our dot here. And so right at that point, it looks like it's at about 40 kilometers.
Okay, and if we trace over to the y-axis for time.
Okay. We have that at about 7 seconds.
So I'll write the P wave over here.
Okay.
So if we have rate equals distance over time, what did we find the distance to be?
So the distance was 40 kilometers in this case.
40 kilometers. And what was the time it took to travel those 40 kilometers?
And that, in this case, is 7 seconds.
7 seconds. Okay, so our P wave velocity.
That comes out to 5.71 kilometers per second.
Ah, okay, so the P wave then is much faster than the S wave.
Right, so this gets into which seismic waves are faster than others, and the P wave is the fastest of the seismic waves.
Ah. So we began this discussion talking about how wouldn't it be nice to have some early warning or some preparedness time so that you could get under a sturdy structure like a table, drop cover, and hold on before the earthquake seismic waves actually get to you.
That's right, so we just calculated the speeds of both the P waves and the S waves. So it would be nice to figure out how much time it would take for those waves, say, to get from the earthquake fault to some city or some other place.
But we know that even though the S wave, as we calculated, travels a little bit slower than the P wave, it has the higher amplitude of the two waves.
Right.
And so it's going to result in the strongest shaking. Here we can look at an example from the 1992 Landers earthquake, which was a magnitude 7.3, one of the larger events that's occurred in Southern California in recent history.
So if we wanted to look at, say, an S wave traveling from the Landers event to, for example, the city of Los Angeles, we would want to know things like the distance between them and the speed at which the S wave is traveling.
Which we just calculated.
Exactly. So then we could figure out how much time it would take for that S wave to reach the city of Los Angeles from the 1992 Landers earthquake event.
So then we can calculate the preparedness time that people would have in Los Angeles to get under a table.
Right. And we should say, though, that this is assuming that we know exactly when the earthquake starts at that location in Landers, and the time it takes from exactly when it starts to the time it reaches the city of Los Angeles. But let's go ahead and measure it here.
Yeah, so if I hold my ruler up to the map, and so I'm essentially going to measure the distance from the epicenter to Los Angeles. So this distance here, and when I measure it on my piece of paper, I get about 8 centimeters on the map.
Okay, so I'll write that up here. This line is about 8 centimeters.
Of course, this is just the map distance, and we need to convert it to real world distance.
Right. So let's go ahead and do that right now. So like you said, we have 8 centimeters on the map.
Right.
Okay.
And then I can hold my ruler up to the scale bar on the map and measure and convert my ruler distance to real world distance. And so I found that about 1.9 centimeters on the map is equal to 40 kilometers in the real world.
Okay, so let's go ahead and use that for our conversion here. So we want to get rid of these map units here.
Yeah, so ultimately we want the units to cancel.
Okay, and so you said that
40 kilometers.
1.9 centimeters, oh right, is equal to 40 kilometers?
Right.
Yeah, that's in the real world. Okay.
So we can multiply these through. 8 times 40 divided by 1.9.
Okay, and so we get, for this one, we get 168.4, and that's kilometers in the real world.
Right, and remember our units are going to cancel, so centimeters on the map appears in both the numerator and the denominator, so those will cancel, giving us what you wrote, kilometers in the real world. So that means this 8 centimeters we measured is actually 168.4 kilometers.
Okay, so now we know the distance.
Right, so if we want to know the time that people would have to drop cover and hold on, we can take our friendly rate equation, but
Okay.
we need to rearrange it.
Okay, so let's write it up here. We have rate is equal to distance over time. Okay, but like you said, we need to rearrange it.
Right, because we're interested in time.
So that means that we want this t, this time variable, by itself on one side of the equation, and the other variables all on the other side of the equation.
Right, so we can multiply both sides by t,
Okay, so I'll go ahead and do that.
and then t is going to cancel because it's in both the numerator and denominator.
Okay, so that means we get, from this above, right up here, we get distance equals r times t.
Okay, but we still don't have t standing alone.
Okay.
So we need to divide through by r.
Okay, let's go ahead and do that. So that gets rid of the r on this side because we want that t by itself, but whatever we do to one side, we have to do to the other.
Right.
So these r's are gone.
Okay, so now this looks right. We have time equals distance divided by rate. Okay, so we can plug what we know about the distance and the rate or velocity of the S waves into this equation.
Okay, so let's go ahead and do that. So we calculated the distance, and that's d, is 168.4.
Right, and then we calculated the S wave velocity to be 3.33.
Okay, 3.33
And that was kilometers per second.
kilometers per second.
Okay, so dividing these through, we find that the time that LA would have to drop cover and hold on would be 50.6 seconds.
Okay, and we'll notice that the kilometer units canceled out
Right.
and the seconds come up to the top, so we have 50.6 seconds.
Wow, so LA would have nearly a minute of time to get under, say, a sturdy table in their office or at their school desk and wait for the shaking.
Right.
But we know in actuality it takes some time for the earthquake to be detected and for a warning system to alert people.
And that's true. And then we know that maybe even though the P waves are less strong, that they will arrive before 50.6 seconds because they're faster than the S waves.